Hi, and welcome to this next video where we'll introduce nonlinear transforms as a method for extending the range of problems or data sets that we can use linear models on. Okay, so let's try to motivate these nonlinear transforms and see what they are. Okay, so in the last couple of videos, right, except for a few videos on learning theory, we looked at linear models as our main method for predictions, except also for the decision trees, right? And in particular, we saw these three different versions of it. We saw logistic regression in the last few videos, where we make predictions that are supposed to be estimates of the probability of a given data point's label being 1. And then we introduced the sigmoid function that you apply to the inner product between a vector of parameters w and the feature vector x, ending up in an expression like this, which gives numbers between 0 and 1. Right, then we looked at also classification, where we saw the perceptron learning algorithm, where we just take the sign of the inner product between w and x, which corresponds to determining which side of a hyperplane you lie on. And finally, we just looked at linear regression, where we just return the inner product as our estimate of the label. And the label here is really a real number. Okay, so these are the three different linear models that we've seen so far. And now what's common to all of them, as you can also see in the previous picture, is right, there's always a hyperplane. And then somehow, right, the estimates are based on the inner product between this unnormalized normal vector of the hyperplane w and the feature vector x. So, which means that somehow, regardless of which of these three models that we're looking at, somehow a hyperplane has to describe the data well, right? So either it has to separate the classes into two, or maybe the distance to the hyperplane should capture a value, the label value in regression, and so on, right? So it really has to be, the data somehow has to be linear, or the dependencies in the data has to be a linear dependency. Which of course means, right, that perhaps we cannot really use these linear models for all types of data. Now, for instance, consider this data set that we have here. So as you can see, right, there's a cluster of points in the center around the origin that belongs to one class, and then you have points outside that belongs to the other class, right? And there's no linear model that's going to do well in predicting the class of any given point here, right? So clearly, if you draw any hyperplane, both sides will have a good fraction of both, or at least one of the two sides would have a good fraction of both types of points. Okay, so linear models are not really that great in this example, at least. So the question is whether we should just abandon linear models, right? So let's look at the example from the previous slide again, just in a little bit simpler setup here, or a smaller example. This data is really very far from being linearly separable. We have these points in the middle that belong to one class, to the +1 class, and you have all these other points around it that belong to the -1 class. So if we run the perceptron learning algorithm on this data, right, it's not going to perform very well. It's not going to find a good hyperplane. And this is actually, regardless of what linear model we try to train, it's not going to find a hyperplane that does well in splitting this data. So, but instead, right, if we look at this plot here, right, it's clear that this seems like an easy data set to learn to predict labels of feature vectors, right? Because clearly it seems that the blue points, the blue class, cluster around the center, and the red points are kind of in a ball further out, right? So somehow it feels like at least the distance to the origin could be used as a feature to classify this data well, right? So, for instance, if I drew this circle here, it's not unreasonable to believe if I get a new data point, if it lies outside this circle, it's probably the -1 class. And if it lies inside the circle, it's probably the +1 class, right? This is not completely far-fetched. So of course, right, maybe you can just try to design a learning algorithm that does well for this type of decision boundary, right? So maybe a learning algorithm that doesn't find a hyperplane, but instead finds a ball and then predicts one class for everything inside the ball and another class for everything outside of the ball. Right? This would, of course, require designing a new learning algorithm for balls as well, right? We have the perceptron for hyperplanes, and we can maybe figure out a ball learning algorithm for finding the best ball, and so on, right? So, of course, this would be great for algorithms designers. There's lots of work to do, but do we really want to have a technique or an algorithm for every reasonable type of decision boundary you could encounter in real data, right? Right, so circles, for squares, for lines, right? We have our own algorithm for each of these types of decision boundaries, and that doesn't seem like the right way to go. So if we go back to these linear models, right, and what we'll see throughout the rest of this video here, we'll try to see how we can modify or adapt these linear models that we've seen in order to actually deal with these other types of decision boundaries, other types of data patterns. So if we go back and think about these algorithms, right, when we train them, the only parameters that we're changing are the parameters in W, right? We're only modifying the weights or the coordinates of this hyperplane normal vector W, which means that, I guess, as we're training the algorithms, we kind of think of the data matrix and the labels as constants, right? We're computing gradients with respect to all the parameters of W, but not with respect to the input variables in X and Y. So these are really just constants. And then we just change W during the algorithm, which means that what we could do is that maybe we could actually change the data first, change X, and then run the algorithm, right? So then the algorithm would still be the same, but perhaps we could change the data before we run the algorithm in such a way that the linear model actually makes sense to use, right? So that's the basic idea in these feature transforms that we'll see. So what is a feature transform? In particular, what is a nonlinear feature transform? So again, if we look at this data here, a nonlinear feature transform is a mapping. It could also be a linear feature transform, but in general, a feature transform is a mapping that takes the original d-dimensional feature vectors and then map them to d-prime dimensional feature vectors. Okay, so it's some mapping that translates points from d dimensions to new representations in d-prime dimensions. So let's see, right? So that's called the feature transform, this phi, and this output dimension RD prime is often denoted by Z and is called the feature space. So this is where the new features lie. Okay, so here we'll just think of it as D prime real numbers, the new features. Okay. Now, what you can do now is that the basic idea in using nonlinear feature transform is that before you start training your linear model, you take this feature transform that you decided on, and then you apply it to all the feature vectors one at a time. So just take every feature vector and map it to, it has D features, and then you map it to a D prime dimensional feature vector instead. And then you run your linear model on these new vectors that you've got after applying the feature transform. Okay, so let's try to see what that could look like, right? So maybe just first to say once again what it actually means is that, well, if we apply this feature transform to every feature vector we have as input, and we can still place them, then we get a new data set, and we get a new data matrix X prime, where each of these new feature vectors are the rows, right? So now it's an n by d prime sized matrix instead of an n by d sized matrix, just having the feature transform vectors as the rows. So let's have an example here that actually works well for this data set that we've seen. So here's a feature transform, right? It has to embed from these data points have 2 coordinates. So it embeds from 2 dimensions. And in this example here, it just embeds into 1 dimension. So it's a symbol, it actually goes to fewer dimensions than we started out with. This is not necessary, but this is definitely possible. Okay, so what does it do? So it takes the 2 coordinates, x1 and x2, and then it computes this nonlinear transform of the coordinates, right? So it takes x1 and squares it, it adds x2 and squares it, and that is this, and you add them up, and that's your new single coordinate in your new feature vector, right? This is a nonlinear transform, right? And you do it beforehand. You can easily you can just compute it from the data. You don't need to know what W is or anything, right? It's just a transform of the data. So what it actually does is that it maps this data set here on the left to this data set here on the right. And to see why that's the case, right? So this is a 1-dimensional data set, and right, the single coordinate, the coordinate of a new point, is just the square of the x1 coordinate and the square plus the square of the x2 coordinate. And this is really the square distance from the origin. Right? If you take x1 squared and add x2 squared, that's the square distance from the origin, which means, right, that the closest point here to the origin before is also the one that's closest to 0 in the new data set. In particular, right, all these blue points are the ones that are closest to the origin, so their square distance to the origin are less than the square distance from all the red points to the origin. So all these blue points here will cluster in the beginning of the positive part of the x-axis over here. Similarly, like the red points here, the furthest one from the origin is the one who has the highest value of x1 squared plus x2 squared, so that maps furthest away from the origin over here. And similarly, right, we can take all these data points and map them, and then we'll get that if you have this new data set here, right, this is actually easy to separate with the linear model, right? It's 1-dimensional, so a linear model is basically just a threshold or a line, and everything before the point and everything before it is one class, and everything after it is the other class. So what we could do now is we could say, okay, we first apply this feature transform to obtain this data set over here. Now what we do then is that we could then run the perceptron learning algorithm, hoping that this data is linearly separable. So we run the perceptron learning algorithm on this new data matrix X prime with this old labels Y. And maybe this finds a separating hyperplane, let's call it W tilde, because it's somehow sitting in this feature transform space. So we find a hyperplane on this data set here. So this could be this one here, right? A hyperplane now is basically just a point where everything on one side belongs to one class and everything on the other side belongs to another class. So we find this hyperplane here just by running the perceptron learning algorithm, because this is a linearly separable data set. So, okay, so let's just, to be completely formal about what's going on here, right? Then let us just remind ourselves that when we run the perceptron learning algorithm over here, right, we want to get rid of this bias parameter. And the way we did it was that we hard-coded this extra feature into the data points that we hard-code to 1 in order to capture the bias. And then we have an extra parameter in W tilde that is just multiplied onto this bias parameter to capture the bias. So basically, this means that even though this is a one-dimensional data set, we add a special first coordinate that we hard-code to 1 for all the data examples. And then the feature or the hyperplane vector here has 2 entries, one that we multiply onto the special hard-coded feature, and the second one that's multiplied onto the X coordinate here. So W is going to look like something like this, right? So the first term is just capturing the bias. Now, okay, so let's continue this example here. So you could imagine, right, that this hyperplane here, if you look at the X coordinate, this is really sitting at the X coordinate of 7. So everything here before is less than 7. Everything above here has an X coordinate of more than 7. Which means that, if we were to figure out the parameters of this hyperplane, here's one valid representation of this hyperplane. The bias is 7, okay? And the parameter that is multiplied onto the X coordinate is -1. Right, so just to see that this would actually represent this hyperplane here, right, you can see that, well, if I take any of these points with an X coordinate of less than 7, then basically we take the 7 as the bias and multiply it on to the 1, which is the hard-coded bias parameter, so we get a value of 7. And then you subtract off this X coordinate, right? And if this X coordinate is less than 7, what we subtract off is less than 7, and we get something positive, so that when we take the sign, we get the +1 class. Likewise, if we subtract something here with a coordinate, an X coordinate that's more than 7, we get a negative number, and we get and the final outcome is a prediction of -1. Okay, so really what's happening here, right? The hypothesis that we're actually creating, right? So what we're doing is we're taking, when we have any vector over here in this feature space, its representation is it has this hard-coded 1, and then as the second coordinate, right, it has this feature transform of the original point. And when we make predictions using the perceptron learning algorithm or linear model, right, we just take the sign of the inner product between this W tilde and this feature transform. So if we write it out, right, the 1 is multiplied on to the first coordinate of W tilde, so that gives us a W1 tilde. And then the second coordinate here, the feature transform, which is this x1 squared plus x2 squared, is multiplied on to W2 tilde. So the actual model that we're really training is this one down here. So you can see this is not a linear model, right? This actually is a model where we're fine-tuning W1 tilde and W2 tilde using the perceptron learning algorithm. But really, we're doing it over the data set or the model that we get actually looks something like this, right? It's actually taking the sign of an expression that looks like this. So if we plug in the numbers here for this W tilde, right, we have a 7 here, and then -1 times x1 squared plus x2 squared. As you can see here, right, this is going to predict positive whenever the squared distance from the origin is less than 7, and it's going to predict negative whenever the squared distance from the origin is greater than 7. So this really corresponds actually to a decision boundary that looks like this purple circle here, so that everything inside the purple circle is going to be a positive prediction, and everything outside is going to be a negative prediction. So really here, we somehow cheated the perceptron learning algorithm into computing a decision boundary that looks like a circle rather than a hyperplane. And this is really all captured by doing this feature transform first, where we somehow map the coordinates of the input feature vectors to new coordinates and then run in a nonlinear fashion, and then run the perceptron learning algorithm on these new feature transform vectors. Okay, here's another example just to finish off. So maybe here's another data set. Again, if you draw any hyperplane, it's not going to separate it well. But here we could at least look at the data, and it seems like here's a feature transform that could work. There are many others, but here's one that makes sense. It's nonlinear again. So given a feature vector, an original feature vector, we could, for instance, take the x1 coordinate and multiply it with the x2 coordinate and then take the sign, which means that basically if the x1 and x2 coordinate have the same sign, then this is going to be positive, and otherwise it's going to be negative, which means that everything up here in this positive quadrant here, right, both the x1 coordinate and the x2 coordinate are positive, so they're going to be mapped to +1. Everything down here is going to be mapped to -1. +1 as well, sorry. They have both negative coordinates, so the product here is going to be positive. Take the sign, we get a positive number. So all the blue points are mapped exactly on top of this one blue point here, and all the red points are mapped exactly on top of this one red point here. Okay, which means that basically we're training a decision boundary that looks like this, right? So we're predicting blue in these two quadrants and red in these other two quadrants. Maybe the important thing to remember again is that if we actually train one of these models using a feature transform, then when we get a new data item that we want to make predictions on, we have to first feature transform it and then use this hypothesis W tilde that we train in feature space, take the sign of its inner product with the feature transform vector. Okay. So this is nonlinear feature transform, and let us just end up with a few considerations on when you should apply this and which things to be aware of. And we'll return to these feature transforms later on in later videos, in particular when we get to cover support vector machines. So just a few thoughts on this. So we looked in the learning theory part of the videos, right, a few videos ago. We argued that if you have a very complicated hypothesis set, right, so a large hypothesis set, basically, then the generalization is worse. At least you cannot really trust as much that the performance that you have on your training data is as good as the performance you have on new data, right? In particular, we argued about this formula here, that if I run my learning algorithm, I find a hypothesis H star, then the chance that the in-sample error and out-of-sample error of this hypothesis H star are within a larger than epsilon apart, more than epsilon apart, is no more than this 2 times m times e to the minus 2 epsilon squared n. And here you can see that the guarantee gets weaker the more complicated the hypothesis set is. So which means in some sense, right, the more parameters you have in your hypothesis, the weaker guarantees you have. Now, we also looked at, well, for these linear models, right, at least if you're using floating point numbers to represent these d-dimensional feature vectors, then the size of the hypothesis set would be something like 2 to the 32d, right? So it's exponential in the number of parameters of the hyperplane. Okay. Now, which means, right, because when we're running when we're running the perceptual learning algorithm, right, we're running it in feature space, right? We have these new d prime features, right? After transforming the original feature vector, we have these d prime new features, which means that we actually have d prime many coordinates or parameters in the W vector that we're training. So, the larger d prime is, the more complicated the hypothesis set becomes, and the weaker guarantees we have on how well we can trust that the in-sample error generalizes to the out-of-sample error. Right. So for instance, right, if we make a feature transform of two coordinates x1, x2, and we turn it into a whole bunch of different features, like maybe a coordinate is 1, maybe one is x1, maybe one is x2, maybe there's an x1 squared, maybe there's an x2 squared, maybe x1 cubed, x2 cubed, x1, x2, and so on, right? So if we just add, it would be easy to just add tons of all these many features, because then, maybe it's very easy for the learning algorithm to perfectly classify the training data. But this means that then there's so many parameters here that learning theory tells us that we cannot trust as well in the predictions that we make. So here's actually an example of this, right? So over here on the left, we have a data set. It's the same data set on the left and the right. There's some blue points and some red points. And, if we try to fit a hyperplane, maybe run the perceptual learning algorithm, maybe we could find a classification like this, where basically we get all the blue points correct, except a single one that's sitting down here. And maybe we also get basically all the red points correct, except for a single red point up here. Now, what you could do is you could take all these original points, and then you could map them using what we call a fourth degree transform, right? So basically you compute the new feature vector would have every single coordinate that's a combination of up to 4 original coordinates, like so 1, x1, x2, all the way up to, let's say, x1 to the 4th, maybe x1 cubed, x2. So any combination where you have up to 4, a total degree of 4. So if we actually do that and run the perceptual learning algorithm, then the right-hand side picture here is actually what you would get out. You would actually get something that perfectly classifies the training data. So here we just kind of drew what the decision boundary would look like, which points if I actually performed the feature transform and use the model that the perceptual learning algorithm finds. The data or the decision boundary would look like this, right? So if I take any feature point, any point with a feature vector lies inside the blue region, it would be classified as +1, the blue class. Anything in the red region would be classified as the red class. And at least intuitively, it would seem that this model up here on the left, I would say there's a bigger chance that this is actually a more accurate prediction of the true label of a point. But it just seems like there are 2 outliers here, and you create these really complicated decision boundaries just to get those 2 outliers correct, which means that maybe if when you get new data, you'll make mistakes. If maybe you'll have points that are sitting down here at the bottom that you will predict as blue, even though they're probably supposed to be red. So this example really shows that it's not really worth the high complexity in the model to just decrease the in-sample error just a tiny bit. Right? So here you just decrease the in-sample error just a little bit to get these 2 points right. You decrease the in-sample error a little bit, but you're now using a really complicated model. So this is something to be aware of. Right? It would seem at least that this model over here has a larger E out than outer sample error. That would be the intuitive guess. Okay, so this is just recapping, right? You should be careful not to introduce too many features in your feature transform unless they're really necessary or unless you have a lot of data, right? Now, another thing to be aware of is that these 2 examples that we saw before, right? We had the ones where the points were kind of close to the origin. It was the +1 class, and the further away was the -1 class. Similarly, like we have the positive and the negative quadrant had the positive class, and the 2 other quadrants had the negative class. What we really did there was that we actually sat down first, looked at the data, and then came up with a feature transform that worked well, right? So one has to be careful here, right? At least if you want some theoretical guarantees, right? Because Hoeffding's inequality basically only works, all these steps that we did, if the hypothesis set H, we're doing this, if you recall the proof, we're doing a union bound over all hypotheses in the hypothesis set, and all of them should be chosen independently of the training data. But here, right, in some sense, what you're doing, if you're looking at the data first and then choosing your feature transform, then in some sense, you're choosing the hypothesis set after seeing the data. So then Hoeffding's inequality doesn't work, right? In some sense, you should think of it like this, right? That if you actually collect some training data, then you actually have a look at it and you choose your feature transform based on what you see by looking at the data. Then in some sense, right, if you take a step back, what you actually do is that in some sense, your hypothesis set is really all the hypotheses that you could have ever thought of by just looking at the data, right? Because you're already making a choice, you're already learning from the data. So which means at least you don't really get theoretical guarantees. So what you could do, and this is if you actually have some domain knowledge, maybe you have some experts that know something about the concrete problem, and maybe it would be reasonable to have this feature squared. Then you should include this feature transform, like maybe square that coordinate, add a feature that's a square of that coordinate, but you should do it before you actually look at the data. This is the most sensible thing to do. Or maybe you should take aside a small portion of your data set, look at that, and only choose your feature transform based on this small portion of the data set, and then you could train on the remaining part. But this basically means you could have experts that handcraft features. This is a sensible thing to do. If they have domain knowledge, they shouldn't really look at the data set beforehand. Right? At least if you want theoretical guarantees, then you should try to avoid this. Okay, so this is a short summary of what these nonlinear transforms are useful for, and now we can use linear models even in cases where the data is not really linearly separable, but maybe there's still a simple explanation that you can capture with one of these nonlinear transforms.